Hello, and welcome back to a video series on MAC 1140 Precalculus Algebra. My name's Sean Perry. These are guided notes number 21 in the series on section 4.3, Geometric Sequences and Series. The first question asks us if a geometric sequence is the same thing as a sequence where the ratio between any two consecutive terms is constant. In particular, if we go from one element in the sequence to the next one, we could do that just by multiplying by r. This is the same thing as saying that a(n) divided by a(n sub 1) is equal to r. We call this the common ratio of the sequence. And it's not too difficult to see that that's the same thing as the definition we gave in previous videos for a geometric sequence, which is where we take the first element and multiply it by r raised to the n minus 1 power. The minus 1 just makes it so that our first term, when we plug in 1 here, gives me an r to the 0, or just 1. And so we just get a sub 1 alone. Essentially, we're saying how many times do we want to multiply by r in order to get to the a sub nth element. For the first one, we want to multiply by r no times, so just times 1. To get to the second element, we would multiply by r once, and so forth. If we know that a sequence is geometric, then finding that r is no different than just taking one element and dividing by the one that came before. In every case for this sequence, that's going to give us a minus 5. So minus 5 is our common ratio. Checking the next one, we seem to be multiplying in the denominator of a fraction by 2 each time, and that's the same as multiplying by 1/2. That makes this a geometric sequence with a common ratio of 1/2. For number 4, they've given us one that's a little bit scrambled. Notice, however, that we could pull out a to the 4 and turn this into an 8 to the n minus 1. The 5 has no power, and so I could just divide out a 1/5 a single time, and this tells me that 8 to the 4 divided by 5 times 8 to the n minus 1 will give me this sequence here. If you don't believe me, simplify this expression and see that we really do get what we started with. Now, writing it in this form makes it obvious that what we're doing is multiplying by another 8 each time. And so our common ratio is 8. If we just plug in some values of n here, or into here, either one, what we'll wind up with is 8 to the 4 over 5, 8 to the 5 over 5, 8 to the 6 over 5, 8 to the 7 over 5, and so on. And that's just these decimal expressions here. For this next sequence, what we want to notice is that we are multiplying by 4 each time to get from one element to the next, and that our first element is 5. That means we would use the following form for our geometric sequence, with a 5 and a 4 placed thus. For number 6, to find the nth term of the sequence, we want to first write this formula, the standard form of the geometric sequence. Now we notice that what we're doing is multiplying by 2 each time, so that's our common ratio, and we've started with a minus 10. So that would give the following form to our geometric sequence. And if we replace n with a 9, we get as follows. 2 to the 8 is 256, and times negative 10 gets me negative 2560. For problem number 7, they've actually picked some kind of special values. They tell me that the third term, look at that. They tell me that the third term is minus 1, and the 10th term is also minus 1. Let's really just ignore these particular values, and I'm going to show you in general how you could calculate this problem. The first thing we want to do is write down our standard form of a geometric sequence so that we can see clearly what's going to happen when I plug in 10 to get the 10th term and 3 to get the third term. Notice that we don't know what r and a1 are, but we do know their outputs when we plug in a certain value of n. Now this tells me that a sub 1 times r to the 9 is equal to minus 1, and so is a sub 1 r to the 2. That's also equal to minus 1. If these were different values, you would just put those different values here. Now, notice that if we take the quotient of both sides, I divide the left-hand side by the left-hand side, and I divide the right-hand side by the right-hand side, what I get is that r to the 7th is equal to 1. Now, this tells me that r is itself equal to 1, and this lets me go back into one of my equations. Let's say a sub 3 is equal to minus 1, and say, well, what is that now in terms of a1? If we substitute these values in and solve, we find that a1 must be negative 1. Now again, minus 1 and positive 1 here are pretty special values for a geometric sequence to have, but you could follow this regime regardless of what these two values were creating a quotient of the left-hand sides and right-hand sides to cancel a1, and then solving for r, and then resubstituting to find a1. This would work regardless of which two values they gave us here. As long as we knew that the sequence was geometric, we know it has this form, and this would work. Here they've given us a1 and r, so we know that our geometric sequence has this form. Now, they ask for a summation formula, so let's actually take a look at that real quick. To start with, let's derive that formula. If I take a look at the sum of the first n terms, that's what we call s sub n. Let's take a look at the special case where a sub 1 is equal to 1. Now, in that case, the first n terms look like this. And if I multiply again by r on both sides, I would increase the exponent by 1 in each place. Now, taking the difference of the left-hand sides and right-hand sides, I wind up with the following: a lot of cancellation except for 1 minus r to the n. Then we could factor out our partial sum and divide off 1 minus r to get the formula for the partial sum, that is to say the sum of the first n terms of a geometric sequence. Now, a geometric series concerns what happens if we take this sum and let it go to infinity. Do we get something consistent? Well, if we have a small r, that is to say an r between -1 and +1, then its powers will get smaller and smaller and go to 0 as n goes to infinity. And if we look at what that would mean for this expression, it means that this term would vanish and we would just get 1 over 1 minus r. Now, in a general sequence that has a sub 1 term, you could imagine just factoring that out and multiplying it against the partial sum formula that we got before. And likewise, if the r is of magnitude less than 1, then we would really just multiply that formula for the infinite sum by a sub 1. And when we consider these kind of infinite sums, we are now discussing something not called a sequence anymore, but called a series. A series is kind of an extension of summation from a finite number of things to an infinite number of things. And it has to be done with a whole lot of caution. We're just going to worry about the convergence of geometric series here and not the full spectrum of the topics that you can cover concerning series in general. No, what we're going to be asked to do is far simpler. For example, here I have a geometric sequence. What is its summation of the first 6 terms? We now have a formula for that. And plugging in our n, we can get the sum of the first 6 terms. Here they've given us an example of the elements, and we have to find out that it has a common ratio. They tell us that it's geometric, so we just need to check 1. To find out the common ratio is 7/6. Now, if we want the sum of the first 10 elements, we take our leading term, 4/7, and we multiply that by 1 minus r to the n over 1 minus r. And when all the dust settles on that, we'll get something about 12.59. For number 10, we want to do something similar. We want the sum of the elements from 1 to 7. So we note that we have a geometric sequence here. Our first term is 6. Our common ratio is a -2. And notice that if I plug all of that into the sum formula, we wind up with these. I need my n to go here, and that's going to give us 258. Here we have an infinite sum, ... and we notice that each time we are multiplying by a fifth. And so this is our common ratio. A fifth is indeed of magnitude smaller than 1, so this infinite sum will converge. And what we find is our a term divided by 1 minus r. a1 divided by 1 minus r would be 2/5 over 4/5, and that's just going to give us a half for this problem. Here we have something where we're going up by multiplying by 4 each time. That means our common ratio is greater in magnitude than 1, greater than or equal to, and so it diverges. Hence, we need not try to find its sum at this point in time. Here we have another series, sum from 0 to infinity now. So notice that the sum from 0 to infinity isn't exactly how things were listed in our problem, but notice they've also reduced the power from k minus 1 to just k. So yes, this is going to converge. -1/4 is of magnitude smaller than 1. But let's take a look at it. Notice that this would be the 0th term. This would have a 0 exponent. This one a 1, this one a 2, and so on. And that means this really does have the same look as if I had increased the lower index by 1 and decreased the exponent. That would still plug in a 0 for my first term, a 1 for my second term, and so on. So notice that these two forms, either starting from 0 up to infinity with a k power, or starting from 1 up to infinity of a k minus 1 power. They really are the same expression, and that's the one that we had this formula for, where my a sub 1 is just 1, my r is 1 negative 1/4, and plugging all of this into our summation formula, we wind up with 4/5. This next one is going to be convergent because the common ratio is less than 1 between -1 and +1. It's of magnitude less than 1. And notice that if we factor out this 4, we could just look at this part. Same thing as before, starting from 0 or starting from 1. If this is k and this is k minus 1, these are the same terms. So we wind up with 4 times 1 over 1 minus 6/7, which is going to give me 1 over 1/7, and times 4, that gives me 28. For this next one, we only have a common ratio of 7/6, but 7/6 is of magnitude larger than 1. That means this diverges, and we need not try to find the sum. This next one's a word problem. It says that a super ball is dropped from 2 feet and then rebounds 8/9 of the distance from which it fell. How many times is it going to bounce before its rebound is less than a foot? I think the nice way here is to think about, first of all, drawing a picture. If we draw a picture, we see that we're going to fall 2 feet and then come up to 8/9 of 2 feet, and then fall again, and then go up to 8/9 of 8/9 of 2 feet, and fall down, and so on. So something is happening involving this geometric sequence with a common ratio of 8/9 here. Our height, where my first height here I am taking to be 2. That is to say, I'm not counting the bounces with this n, I'm counting each peak of how high the ball is above the ground. It starts at 2 when n is 1. This would be 0 and give me a 2. That's the first height, okay? Now, when will that be the case? Well, when this 8/9 to some n minus 1 power is going to be less than a half. And I think the easiest way to do that is just to plug these values into a table and see where it drops below a half. We can see that after the first height, we get our first bounce. After the second height, we get our second bounce, and so on. And after the 6th height, we get our 6th bounce. And then after that, it comes up just shy of 1/2. And that was the criteria for this original thing to be under a foot. And so we are looking at 6 bounces. They say, how far will the ball travel before it comes to a rest? So what we're basically being asked to do here is see how far it travels going down, and then up, and then down again. We want to add up all these ups and downs. The first fall travels 2 feet, but then after that, it's going to travel each one of these distances twice. So what does that mean in terms of the falling and the rising here? Well, we could look at each one of those as a separate geometric series and then add them together. The first one starts with a value of 2, and then the next pink distance would be 2 times 8/9, and then 2 times 8/9 squared, and so on. So we have a geometric sequence of this kind here. We're taking the nth partial sum, and that taken to infinity would give us this geometric series here. Now, on the other hand, when it rises back up again, we could consider this as being another geometric series, and this one starts at an initial value of 2 times 8/9. But then we would have another geometric series, which we could evaluate both using the formula. And if we do that and just chug through the fractions, we will find an answer of 34. All right, that's going to do it for this video. Thank you very much for your patience and have a great day. Good luck with your studies. I'll see you in the next one.